In this video, we'll talk about vector-valued functions. A function of the form r of t equals x of t, y of t, z of t may be viewed in two ways. It is a set of three parametric equations that describe a curve in space, and it is also a vector-valued function, which means that the three dependent variables x, y, z are the components of R, and each component varies with respect to a single independent variable that often represents time. So here is a description of a picture of R of t. So a point x of t, y of t, z of t on the curve is the head of the vector R of t. All right, so let's remember this. If we write R like this, it means vector. If, and in the book, it's usually written with bold. So they do write R, but it's bolder than the other letters. That means vector as well. So point x of t, y of t, z of t on the curve, it's the head of the vector R of t equals x of t, y of t, z of t. The entire curve is represented by the vector value function R of t, which is of these coordinates. So the notation, the general vector valued function notation, it's R of t. You see it's bold, or you can write it R of t. I think it's easier when you represent that on the paper to write it using the arrow on top. So it's f of t, g of t, h of t on component wise, and you can write it using the unit vectors for each axis. So f of t I plus g of t j plus h of t k, where f, g, and h are defined on the interval t is between a and b, including a and b. The domain of R is the largest set of values of t on which all of f, g, and h are defined. So let's try to solve a problem. Find a vector function for the line passing through the points p of coordinates 2, negative 1, 4, and q of 3, 0, 6. So let me just quickly plot this in 3D. So we draw a 3D plane. We have x, o, y, z. P it's of coordinate 2, 1, 2, negative 1, so that would be this way. So this would be, and then 4. So let's say this is 4. So this would be P. Let's make this dashed. And Q, it's 3, 0, and 6. So PQ would be this vector. And we want to find the vector function for the line that passes through this point. So here is the line that passes through PQ, and we want to find its vector function. So basically, we want to find when it goes vectors from the origin to the line of PQ. It's a little bit hard to see because of the location of PQ. So first of all, the vector v of PQ is given by 3 minus 2, 1, 0 minus negative 1, 1, and 6 minus 4, 2. So this is vector PQ. Now, the line is described by R equals R naught plus TV. V we just found. This V is this one. R naught are the coordinates of the initial point of P. So R, or vector R of t, let's make these vectors, is R0, which are the coordinates of P, 2, negative 1, 4, plus t times the vector v, which has the components 1, 1, 2. So rt is given by t plus 2, t minus 1, and 2t plus 4. So this is the vector function for the line that passes through the points. These are the x of t, y of t, and z of t. And if you give to t the value 0, you're going to get 2, negative 1, 4, which are exactly the coordinates of P. If you give to t value 1, you get 3, 0, and 6, which are the coordinates of Q. And if you give other values for t, you are going to get points that are on this PQ line. So let's find the vector function for the line that passes through the point P of coordinates 2, 3, 7 and is parallel to the line R of t equals 2 minus t, 4 plus t, and 1 minus 2t. So the direction vector for the line, or for the function that we want to find, is going to be negative 1, 1, negative 2, and these values are given by the coefficients of t from here, because if the lines are parallel, then their slopes are equal, and so the vector function of line L is going to be R equals R naught plus VT. So R naught is given by OP, and knowing P is going to give us 2, 3, 7 plus V is negative 1, 1, negative 2 times T, so that is equal to 2 minus t, 3 plus t, and 7 minus 2t. So this is the vector function. R of t is given in terms of x of t, y of t, z of t, and we can say that t is any real number because there is no restriction for any of these functions. They are linear. Let's do another problem. Graph the curves described by the following functions indicating the positive orientation. R of t is equal to t to t for t between 0 and 1. So let's make a table of values. And let's put t and then R of t, which is t and 2t. So if t is 0, the first coordinate is going to be 0, 0. If t is, let's put 1 here, it gives us, let's say better, instead of R of t given like that, let's write it in the form as x of t, y of t, like that, where x of t is t and y of t is 2t. So if t is 1, we get 1 to the coordinates. If, let's say we have 0.25, 0.5, and 0.75. If t is 0.25, we have the coordinates 0.25 and 0.5. If t is 0.5, we have 0.5 and 1. And 0.75, and 2 times that, 1.5. So now let's plot these points. X, so y, and so we have 0, 0, then 0.25. Let's say this is 1, and we split it in 4. So we get 0.25, 0.5, and again here 0.5, 1, 1.5, 2. So 0.25, 0.5 is this point, 0.51 would be this point, 0.75, 1.5, and 1, 2. So basically the curve, it's actually a straight line, it's actually a segment, right? Because it's just between 0 and 1. And the positive orientation, well, it goes up from left to right. Let's see this problem. Graph the curves described by the following functions indicating the positive orientation. R of t, write a vector, it's cosine ti, j, and sine of t. T is between 0 and 2 pi. So I'm going to make a table of values, t, and then we have cosine t, 1, and sine t. So if t is 0, we get cosine of 0, 1, 1, 0. So this is the triple. If t is pi over 2, we get cosine of pi over 2, which is 0, 1, and sine of pi over 2, which is 1. Pi, cosine of pi, negative 1, 1, right, this middle one, it's 1 all the time. And then sine of pi, which is 0. 3 pi over 2, cosine of 3 pi over 2, 0, 1, and sine of 3 pi over 2, negative 1. And 2 pi, we go back to the 0, so we get 1, 1, 0. So let's plot this. X, O, Y, Z. Made a better picture. And now let's see. Let's plot 1, 1, 0. So 1, 1, the intersection would be this one. So 0, so that would be this first point. 0, 1, 1, 0, 1, and then 1 would be this point. Negative 1, so negative 1, parallel, right, to the original one. Negative 1, 1, and then 0. So it would be around here. Then it would be 0, 1, negative 1, 0, 1, and then negative 1. Just going down. So it would be 1, 1, 0, 1, 1, 0 back. So basically, I can put some more points to get a better idea. So maybe I should put, I don't know, pi over 4. So that would give me cosine of pi over 4, that's square root of 2 over 2, 1, and sine of pi over 4, square root of 2 over 2. So that would be square root of 2 is 1.7 divided by 2, 0.85, so it would be somewhere here. With 1, it would be this point, and then going up a 0 point something, so it would be somewhere here. So the graph looks like this. To find the orientation, I placed here the points for different values of t. So this one would be t equals 3 pi over 2. So actually the direction that it goes in is this one. So it goes this way. And let's do a couple more problems. So let's find the limit of a vector valued function following limit. To do that, we're actually calculating the limit for each component. So its limit as t is approaching pi over 2 as cosine of 2ti minus limit as t is approaching pi over 2 of 4 sine of tj plus limit as t is approaching pi over 2 2t over pi k. So let's calculate each of them. cosine of 2 times pi over 2, that's cosine of pi, that's negative 1i, minus sine of pi over 2, it's 1, so we get 4j, and then we have 2 times pi over 2 over pi, so that is equal to 1, so we get plus k. So the limit is negative 1, negative 4, 1. And let's solve one more problem. Find the domain of the following vector valued functions. So the domain is actually given by the largest interval on which all these functions are defined. So let's take a look at each of these functions and find their domains individually. So square root of 4 minus t squared, for this to exist, we have to have 4 minus t squared greater than or equal to 0, which means if we set t and 4 minus t squared, if we set it equal to 0, this gives us t is plus minus 2. So we put here negative 2, 2. We have to put them in the order. They are on the number line. In between negative 2 and 2, we have positive signs. Just give some values, like 0 is going to produce 4. 1 is going to produce 3. So we have positive, and outside we have negative. So the domain of this function, it's actually negative 2, 2. So we have to keep this information because we'll need it. Then the next function, it's square root of t. So this means t has to be greater than or equal to 0, which means the interval on which it is positive is from 0 to infinity. So let's keep this information as well. And then we want to discuss 2 over square root of 1 plus t, which means 1 plus t has to be strictly greater than 0, just because setting equal to 0 is going to give us 0 at the denominator, so we don't want that. So t is greater than negative 1, which means the interval we are talking about that the function exists is negative 1 infinity. So we want to find the interval on which all these functions exist. So we are going to intersect all these intervals that we figure out here. So negative 2, 2, 0, infinity, and negative 1, infinity. So the place where all of them overlap, the black line, the red line, and the blue one, is this one. So the domain is given by the interval 0, 2. On this interval, all these functions exist.